Hello, good morning, good afternoon, and good evening. I welcome you at Vector's PCT webinar. We are talking today about the topic developing a mixed-critical AUTOSAR Adaptive ECU with safety and security by design. This is a joint webinar of Vector Informatik and our partner SYSGO. Our guest presenter today is Chris Berg from SYSGO. The other presenter today is my well-known and popular colleague of technology, Ingo Niklas. And last but not least, my name is Winfried Schröder. I'm responsible for the moderation of this webinar. Let us have a quick look at our agenda for the next hour. At first, I will give you a very quick overview about Vector's VectorCast solutions. I will hand over then to Chris Berg and his presentation. This will be followed by a technical presentation from Ingo, where he shows us how VectorCast supports safety software development. At the end of this webinar, we will answer your questions. Please use the Q&A window to ask your questions at any time during this webinar. So, I'd like to start with a few facts about Vector. We have 26 subsidiaries in 12 countries and more than 2,500 employees today, which support more than 7,500 customers worldwide. Let's have a look on the history of Vector and VectorCast. As you can see on the time being, the first release of VectorCast was built in 1992. From day one, it was designed as an embedded software testing solution for safety-critical applications. The first version of VectorCast supported Ada, as it was the most popular programming language in the avionics industry, but in the following years, VectorCast supported other programming languages, operating systems, and compiler combinations. Because of the testing requirements in the functional safety standards like DO 178, ISO 26262, IEC 62304, IEC 61508, or SUNLAC, VectorCast is used in all these industries today to verify that the code is well tested. VectorCast is testing solutions for all phases of testing, from low-level software testing to full system testing. Testing can be done natively on a PC or done on a target hardware at all levels. The VectorCast products reside on the bottom and right side of the V where testing takes place. On the left side you see that VectorCast integrates with other tools you probably have in your development environment, and it supports almost every embedded compiler. VectorCast encourages a correct, complete, continuous approach to software testing. Code correctness and a full tested code is the basis for safety-critical software. Testing should be done early in the development process and often. VectorCast supports automation, dashboards, and integrations with other tools like Jenkins, for example. It is always valuable to see where you are with your test process and think about where you want to be in the future. Different organizations are at different places across a wide spectrum. We are going to help you to reduce the time it takes to test, to increase the test frequency, to expand the responsibility of developing quality software within your organization, and to increase the amount of testing you have automated. VectorCast has features that optimizes values in all these areas. So, this was my quick introduction in Vector solutions for software testing. I now pass the microphone and the desk to Chris Berg and his talk, how to develop a mixed-critical AUTOSAR Adaptive ECU with safety and security by design.
Thank you, Winfried, for the introduction. So I hope my screen is visible.
Yes.
Thank you. So again, hello and welcome to everybody to this webinar. I am Chris Berg from SYSGO. My function at SYSGO is a solutions architect. I deal with the technical pre-sales part of the company, and I am responsible for our automotive customers worldwide. Today I want to talk about developing a mixed-critical AUTOSAR Adaptive ECU with specific regards to safety and security by design. So let's see what we will look at today. We will have some motivational slides to get an idea of what we are talking about. I then want to introduce the so-called MILF concept, as well as giving you some insight into the adaptive AUTOSAR from Vector and its integration with the PikeOS operating system. So let's start with a couple of words about the company, SYSGO. SYSGO was founded in 1992 in Germany and has since become a leading provider of operating systems in Europe. We have several offices spread around Germany, France, and the Czech Republic. Since we are very heavily focusing on safety and security certification with our products, most of our engineers actually also have experience in these areas and have dealt with projects in the certification areas in different aspects of the design. Core competences of the company are operating systems and hardware-software platform integration. We focus specifically on avionics, automotive, and railway industries, as well as space and medical. Since 2012, Thales is the owner of the majority of SYSGO shares, so is the mother company, and we are an independent group of Thales since then. So let's get started with some more information about our connection to Vector. In 2017, we formed a joint venture between Vector and SYSGO in order to create a uniform and consistent AUTOSAR adaptive platform, also with the background of joining the tools of both companies to present a single, easy-to-use IDE for the customer. For certification aspects that go beyond this scope, SYSGO can provide its expertise if that is needed by companies. So let's have a look at typical E architectures of a modern vehicle today. We see that we have quite a number of different ECUs in a modern car. Most of the architecture is driven by requirements arising from automated driving, car-to-X communication, as well as the need to deploy applications even in the aftermarket phase. So once the car is on the road and in use, we still want to do updates of the software. We want to add new functions, more functionality while the car is in use. So this is driving a lot of the ideas about the architecture that is in the car today. Of course, also you want to consolidate smaller ECUs to start to reduce the number of hardware you actually have to put into the car. And so we typically see two different types today. The smaller, low-performance I/O control units, usually responsible for certain sensors or actuators around the car that then are connected to higher performance, so-called domain controllers, that then do some more of the heavyweight lifting and calculations, such as data fusion and trajectory computations and other things. So today we will focus more on these central devices that have quite powerful SoCs that run operating systems and run the applications in the car. An example of these SoCs that I see are widely used at our customers is the Renesas R-Core H3, and you already see with 4 Cortex A57 and 4 A53 cores, it's quite a big and powerful SoC. The Xilinx Sync MP SoC is also quite well used. It also has 4 A53 cores, so quite performant systems. And the challenge is here to be able to execute applications with different criticalities or ASIL levels, because now that we have so much computational power and we want to integrate more and more things onto one CPU, one SoC, we have the challenge of separating these things and making sure that different applications run smoothly beside each other. So a system could look like this one. Just an example, you might have one part that runs an Android with applications that are available to the users. You might have the need to run at the same time on the system a part that is booted very quickly and early so that you, for example, can display rear view camera pictures. You might have safety critical needs here running in classic AUTOSAR to manage your cluster or other things that have safety requirements, unlike the Android part, which probably does not need any safety certification in such a system. And you have several other partitions that would need you would need to provide specific services or other monitoring functions to maybe check the state of the ECU and other things. So here you already see that we have many different types of applications that we want to somehow run on the same system. With these heterogeneous setup, we have the following challenges. First of all, we need to somehow share the resources. We have CPUs, we have memory, we have I/O devices, and everybody wants a part of that. So we need some application that is able to control and allow sharing of the resources. So we need some kind of resource partitioning. The other big domain is time sharing. Again, we have multiple applications. Some might have their own core available. Some applications may be sharing cores. So an operating system needs to take care of applying or supplying enough computation time for all the applications that are running on the system. So the solution is needed for the time partitioning as well. In order to create a safe and secure system, we have been working on something called the MILS concept. It's actually a concept that has started fairly early in the 70s in a book from Seltzer and Schroeder about protecting information in computer systems. So you see that this is not only a modern day challenge that we have, the security of computer systems. It has already started fairly early in history with people making ideas about how to handle this. In 1981, actually, Rushby developed a concept called the separation kernel. This is also what PikeOS implements today. And then, as you see here, development continues, mostly US-based until around about 2012, at which time development in the US somehow is superseded by some of the European activities, and a lot of things have been happening since then here in Europe. There is a community called the MILS community. You see that a lot of well-known companies are part of this community. So this is the MILS concept is something that is supported by widely across the industry and is a very acknowledged way to set up these kind of systems that we're talking about today. So what does MILS actually mean? It means multiple independent levels of safety or multiple independent levels of security. So it's actually an architecture idea of how to support the coexistence of applications of different criticalities. So you could have applications with low criticality, medium, high, and you have defined communication channels between them. And on this, with this kind of separation, you guarantee that, or you want to start partitioning a system in a way that is handleable and you can actually oversee and understand its individual parts. So you want a verifiable separation mechanism, and you also want to create some kind of controlled information flow. So how do we go from the architectural to the actual implementation? We call this refinement. So we have the idea of how to actually set up a system, how to architecture it, and then we transport that into an actual integration phase where we need some kind of MILS platform, which is usually a separation kernel. So a kernel, microkernel usually, that provides a very strong separation between what is called partitions. You see these here. And so each of these applications or different criticalities then is put into its own partition. You also define communication channels that are allowed between partitions, such that you actually really implement what the architecture up here defined. So once you have this in effect, the MILS platform actually guarantees your separation, so you can go back to your abstraction layer because you now know that you can work on the individual parts of the design without being without needing to take care about interference from any of your neighboring applications. To help you build this kind of architecture, there are templates available. You can actually download them for free from the MILS community website. These are useful so that you don't forget any of the steps. You have all the things and checklists available there to help you architect a system in this way. So how do I get from design to a runtime system? Mostly if you start architecting a system, what you do is you automatically somehow separate things into blocks, and there's white space there, and usually you have something in mind, and the white space actually means something. White space here in this phase of design means that things should not happen here. You have blocks, we have applications, you have different communication channels between these blocks, and you don't want any of those blocks like breaking out and doing something on their own and spilling into this white space. So white space is actually a requirement, meaning nobody goes here, nobody changes the communication channels. So the MILS architecture and the idea of separating different things from each other helps on the security way, because often when you start a design, you already consider that things are separated as you architect them, and this is already a requirement that you have applied. So the MILS concept helps you actually in a structured way to secure, or in a structured way to approach your security by figuring out how to securely partition and control the information flow. On the safety side, again, partitioning also helps you ensure safety concepts, because now if one of the partitions fails, you can isolate those faults and keep them contained in one of the partitions, and you don't need to worry that any of the other parts of the system are influenced by that. So we have some kind of non-interference, and this has already been successfully implemented and shown in different architectures and implementations. Some of them in the avionics, such as the IMA concept. IMA is the integrated modular avionics, so especially the way that avionics guys integrate many different functions into their designs, and we see this here, for example, implemented in the Airbus and A380 and A400, but also in several automotive projects yet. The third leg that comes from separation is a much easier integration, because now due to the separation of different parts of your system, you can individually look at the partitions and create, for example, parts where you have a guest operating system. You can externalize other functionality and have third parties develop software, for example, with code generation tools like MATLAB or Simulink and others. So again, you only need to know about your part. You know that you're separated from others, and you can very easily pinpoint malfunctioning because of the individual and independent behavior of each of these partitions. How does this tie into the AUTOSAR world? So first of all, let's have a look at what and why do we need a new AUTOSAR version. Mainly because we have new requirements arising. We have highly automated driving that we want to support. There is new communication methods like Car2X. We have connected vehicles that exchange data with the cloud, talk to other cars, and so we need a more flexible system that is able to handle these new communication technologies, as well as being able to dynamically load new applications, new features, is able to update, because today, if you look at your phone, I mean, you exchange that pretty much once a year or every 2 years. With a car that you buy, you keep it for 10 years, but the software is still the same from the day you bought it. So that needs to change in today's world, especially when you're connected, because connectivity always gives you the potential of being attacked from the outside. So update is very important here, as well as the heightened security needs arising from automated driving, where you really need to be sure that your safety requirements are in place. So previously, as you probably know, the AUTOSAR Classic platform is a very static kind of implementation. You have to define everything during configuration time. On the other hand, it can be certified to very high criticalities, so very high ISO levels, ASIL levels, and its demand on the hardware is quite low. On the other side of the spectrum, we have infotainment systems that usually have no or only QM rating, but have very, very high performance and not a lot of real-time requirements here. So there's something missing in the middle, something that actually has parts of both worlds. So is at least certifiable to a certain safety level and has some real-time behavior, as well as being able to run on higher performance platforms. So this is then AUTOSAR Adaptive, the architecture. You see here that different applications are available. They shall run in their own protected address space. They communicate only via API to libraries that are provided by the Adaptive Platform Foundation, and the communication between applications and applications to the system or to other ECUs is done by a specific inter-process communication setup. So how does the adaptive AUTOSAR tie into the PikeOS platform? Well, if you remember the architecture slide, we're saying that, okay, we need to separate applications, we need to separate and different criticalities due to the Mills concept. So Vector has chosen PikeOS to be the foundation of or running adaptive microcontroller on PikeOS as one of the Mills foundations. The PikeOS provides you with the resource partitioning, so it actually gives you containers that are able to execute different applications. And PikeOS also takes care of the time partitioning, so that tasks that are assigned to different partitions get enough runtime to complete their jobs. So PikeOS is building the foundation actually to and guaranteeing freedom of interference as required, for example, by the ISO 26262. So we have a separation kernel, and now we have the AUTOSAR Adaptive idea. So how does this look if we put both of them together? So remember the architecture slide, we had the AUTOSAR Adaptive Services, the AUTOSAR platform, which would then be located in one partition that is separate from all the others. We had the requirement that we want to run all the adaptive AUTOSAR applications in their separate address spaces. So essentially every application gets their own PikeOS partition, so it's separated from each other. And then this would be the AUTOSAR part, and then on the other side, you still have the possibility to have user-defined partitions, so you can add any number of partitions that can support other systems that are outside of AUTOSAR Adaptive. So PikeOS gives you a lot of flexibility to enhance and extend the system to match exactly the needs that you have. So now that we have separated everything, we also have to take care of the communication between different parts of the system. So here we apply a specific kernel module, kernel driver that provides the adaptive platform with IPC service, so that the adaptive AUTOSAR applications can talk to the relevant services on the adaptive platform. So here we have a nice example for implementing the Mills architecture, as we have taken a architecture that has certain separation requirements and have moved them in the refinement phase to actually an integration and implementation on an actual separation kernel. Another requirement for the AUTOSAR Adaptive platform was that you wanted to have dynamic applications. So also this is possible. You can create and start and also stop applications in their respective containers. There is a specific execution manager available on the platform that is able to load and start as well as stop applications at runtime. So also this part of the requirements has been fulfilled with this setup. So towards the end, let's see what is about the assurance. So the assurance means that you want to prove that your system is safe and secure. And one thing you really don't want to do is you don't want to try and develop assurance of integrated system while including all its components. So by all means try to avoid a monolithic approach because it's just very, very difficult for larger systems. And difficulty always directly means that it takes a long time. It always means that it is expensive. So try to separate different parts into smaller subsections and try this divide and conquer approach. And this is specifically also what the MILS approach is, dividing things into handleable assets. So now if we really do a decomposition of the platform, we can say, okay, we can do the assurance of the platform on its own. We can do the assurance of individual applications on their own. And we can do the assurance of the integrating architecture of the ECU. So now we have different parts that can be handled individually, that you can understand, that are manageable, and the system integrator is then responsible only to actually put things together and is more interested in the sum of all these actions to find and generate the assurance for the complete system. Again, transferring this to what we have shown here with the AUTOSAR adaptive approach. So we applied the MILS approach to achieve a compositional assurance. So we have the PikeOS separation kernel. That's one of its own functional blocks. We have certified PikeOS both for safety and also in security certifications. So that is one building block you can use. You don't need to do this yourself. You can rely on the work that we have done. The same is true for the adaptive platform, which is then treated as a user application within PikeOS, but it is also assured on its individual parts. So now pretty much only the applications that need to be tested and certified are left. So this is then something that the user can do by himself, but then he can really concentrate only on these applications. And this is also what the second part of the webinar today will be about, testing these parts and being able to certify the new things that will be added to the system. So now we also are in the position that when we add new applications, we only need to really test them and certify them to their to the level that's actually needed. So we don't need to go and certify everything to the highest level that the system is capable of, but only to what each part is really requiring. So in the end, we can then put together a complete system assurance based on the idea that we have a non-interference, which is guaranteed, so that we can really say, because there's no interference between the applications, between the parts of the systems, this is the reason why we can actually look at the parts individually, and putting them together doesn't change anything in their behavior. Now, using the MILS approach, we are able to put together very complex systems without really getting out of hand with the amount of work and the complexity that arises from such big systems. So in summary, presented how to design a mixed-critical AUTOSAR Adaptive ECU by separation, by using a separation kernel. We have showed how to showed critical and enabling components for mixed criticality. This is the MILS concept and the separation kernel. And we also explained how an assurance case is built for a mixed critical ECU and how this is applied in this area. Just one last slide of acknowledgement. Some of this work has been funded by European and German programs. And with this, I want to thank you very much for your attention. Let's see if there are any questions that we will answer after Ingo's talk. So now, again, thank you, and I want to pass over to Ingo for his presentation of the VectorCast tool.
Yeah, thank you very much, Chris. I have the honor to show you a little bit of VectorCast. I usually get told that I speak too fast, so this time I will try to talk slower. So I hope that, yeah, it's not too fast. I will show a little bit of VectorCast, and if you already know VectorCast, then I hope it will not be too boring for you. I will show some of the newer and advanced features like probe points and call coverage by analysis. So maybe this is of interest for you, even if you know VectorCast already. In the meantime, feel free to send questions to Chris. There is a drop-down in the Q&A window where you can select whom you want to ask the questions so that we know who should answer them. We did some webinars already together with SYSGO in the past. I think it was 2017, where we showed how we can use VectorCast to do tests on PikeOS. So that's perfectly possible, but for this demo, I just show how to run test cases in a host environment on using a GCC compiler. If you are interested in those webinars where we show how to run tests on PikeOS, then I'm sure they can be found in the World Wide Web, because the World Wide Web doesn't forget anything, so it will be somewhere. What you should see at the moment is VectorCast Manage, and I created a project with mixed critical parts. So some of them are ASIL, which is the highest criticality in ISO 26262, as you are probably aware, and some are just of the criticality of QM. Additionally, I have a node that uses a GCC compiler for the programming language C. And then I also have an example with C++, where in the end I will show how to work with C++. On the right hand, we see an overview over the built environments and the status and how much coverage we got, what the execution times were for running the test cases, which obviously is pretty quick. The build times are longer, so if I would want to run all test cases and create all test environments, this would take some minutes. Fortunately, with VectorCast, we have a way to just incrementally build, to do a change-based build and to just build those environments and run those test cases that need to be run because source code changed or because test cases changed, which is not the case. So this is very quick. If we look at those reporting windows, for example, the metric table, we also have a code coverage summary, which is of interest because it shows what are the files that we tested, what are the functions or the methods that are defined in those files. And it also shows the cyclomatic complexity, which is this capital V and the small g. And it shows the coverage that we achieved. So sometimes it's interesting to see what are the most complex functions in my project. We can sort for the cyclomatic complexity, for example, and see that the function with the highest complexity in this case is a function called placeorder, which is probably not a surprise if you know VectorCast. And it does not have any coverage yet. We have 0% coverage, so this is definitely a place where we should add some more test cases, add some more coverage put our focus onto this function. So how do we do this? We can simply create an additional unit test environment for the C file manager in here by right-clicking the node and say we want to create a unit test environment interactive. The nice thing is we inherit the compiler settings, we inherit the call coverage settings. Because we are in the area of ASIL-D, we want to measure statement coverage, branch coverage, and MCDC coverage. The compiler is already pre-configured. We are using the MinGW C compiler, and there is a list of other compilers that we would support, but we don't need to care about that at the moment because we are inside the managed project and already know what the compiler is. So all we need to do is type a name, which can be, for example, UUT, because it's a unit test environment for a C file called manager. And then we pick the file that we want to test, and we say build. So that's all we need to do. VectorCast will create a framework around the C code with a driver that calls the functions under test, with stubs that are automatically created for functions that are implemented outside of the unit under test. And then we get a GUI that allows us to create test cases. So here are the function, and this is the critical function, the place order function with the highest complexity. We can create test cases for the function with a right click and insert test case. And then we get an additional window that allows us to enter input data, for example, for the interface parameters. We can access global variables if we wanted to change the environment of the function. If we wanted to change global variables, and we can also check output data or check how the function changes global variables. We analyzed the interface parameters of the function. So in this GUI, we can, for example, select something to eat. In our case, this will be a lobster. And then we also have access to the stubs, and we can tell the stubs to check values. That means if the stub is called, it will verify if the parameters that are passed to the stub are matching the expected values. And we can also tell the stubs to return specific values, for example, a waiter. So like this, we can define input values and expected values, and then dynamically execute the code. In my case, this runs on Windows. In other cases, it can be on an embedded device or on a simulator, emulator, or wherever. We see an execution report. We see that the test case passed. And we can also look at the code coverage and see how much coverage we got. Did we get code coverage on the complicated part? Are there any paths we didn't execute yet? So we see different colors. Red is the color for not executed lines and green for executed lines. And we also have the color of orange for partly executed. Like in this example, the if statement was executed only with the outcome false. When you create test cases, it's always a good idea to do functional tests first. Do not focus on the coverage. For that purpose, we have an interface to requirements management tools. For example, we can import requirements from DOS or Polarion or Codebeamer or PTC Integrity or other tools. In my case, I used just a CSV file where I imported the requirements, and then we get a list of requirements having an ID, a title, and a description. And for the test case, we can link the requirements to the test with a simple double click. And then, for example, we can check what the requirement tells us, what the expected values would be for those input values, and then do a functional test. I will use a shortcut. I will automatically create test cases just to get more coverage on this file. This is not what you would usually do. but it is available, and you could, for example, use the automatically created test cases to get a good amount of coverage, then take the automatically created test cases and link them to requirements just with a double click, and then derive the expected values from the requirements. The interesting thing in this case is we automatically created test cases that should have gotten us coverage, but there are some lines that were not executed or that were not covered. So here's one example. We have an if statement that is always false, so we will probably never get coverage for this line. And here we have an example for MCDC coverage. There is a check whether the total amount what we have to pay is bigger than 12. And we also check whether there is a discount for this table. And then the check total is reduced. But unfortunately, the developer initialized the discount to false. So even if we take a test case that executes the line, like for example, one of those, place order .001, if we change the global variable to be true, so that means the people should get a discount, and we run the test case, then we will not get coverage on that line because the code changes the global variable always to false. This is one example where we can use ProPoints to change the global variable. For example, I can do this right after it was set to false, or I can do it right in front of the if statement, so it doesn't matter where I add this line. I just add a ProPoint to the code. A ProPoint can be any kind of C code. For example, I can enter the command to set the global variable to true, just like this. And if I activated the ProPoint, then it would always be injected into the code. That means it would always be active for all test cases, which is not necessarily what I want. Maybe I just want it for one test case, for example, for my place order test case, .001. So we have some additional utility functionalities that we can use together with the ProPoints, and one of them is test name equals. So if I add an if statement to my ProPoint saying only if the test name equals place order .001, then I want to have the discount enabled, then we will still get the coverage on the false path and not always have discount true. So once this is enabled, we should see that when we run all test cases, we should also get coverage, as we hope, for the true part of this discount decision. So by the way, if you have to measure MCDC coverage, then there is some help from VectorCast. We do an analyze on every decision point in your code and show a table where we show which test cases you would have to run to get MCDC coverage. So this was the example how to get coverage using ProPoints. The other line that we did not cover is this if false here, or this if 0, and we can enter whatever ProPoint we want. We will not get around this if statement. So this is maybe an example of where you can use covered by analysis. Covered by analysis allows you to manually add comments or to manually add coverage and comment the coverage that you entered. For example, we can say this is necessary, and we did a review meeting, and these are the people that helped doing the decision, and the code is there, and for some reason we disabled it, but it should still be in the code. Then after we saved, we can look at one of the reports. For example, one of the reports. Let me look at the coverage first. In the reports, we will show the line as being covered in blue. And in the metrics, we will see that we make a difference, a distinction between lines that were executed or that were covered by execution and lines that were covered using the analysis editor. So here, when we look at the aggregate coverage report, you see that the line is marked as blue in the as the line. And when we look at the metrics table, then we see that we do the distinction for the place order function, that we now have 100% coverage, and we have one line from analysis, and the rest comes from execution. So far for this test environment, the last thing I want to show is the C++ thing that I promised. We can go to this test environment. You may see that it is different from the others. We do not have any test cases, and we do not have any coverage. And when I open it, then we see that there is no testable functions, no methods. When we look at the source code, we see why. This is an example of a template. So how can you template or test template functions? With Vectorcast, we have the option to say we want to add user code. For example, we can add appendix user code and create or derive a class from this template in unit appendix user code. For example, we can create an instance of the template class for an integer object. And when we now rebuild the environment, then Vectorcast will add this appendix code to the real CPP file and then build the framework around this code. That means we will have an instance of the template class using integer, and we can create a test case on the instance of the template class. And to make this quick, so this is an example of a stack implementation. It is not enough if we wanted to test the push, for example. We first need to call the constructor, and if we wanted to test the pop from the stack, then we would have to push something to the stack. So this sounds like a complex test case. Let's create the stack, let's add some elements, and then test whether when we pop elements from the stack, whether this is what we would expect. And this can be done using compound test cases. So first we create a test case on the constructor, then we create a test case on the push, which can be, for example, 1, 2, 3, 4, 5 elements. And then the pop just is called, and we would expect that it returns element number 5. If we put this all together into a compound test case, that means we first create the instance, then we push 5 objects, and then we pop 1. And when we execute, we should see that it fails because I did something wrong. But at least we see that we executed the tests one after the other, and we see that we have an instance and that we executed code, and we can look at the code coverage and then try to find out what we did wrong. So far from my side, I hear Winnie in the background. That means that I'm over the time. Maybe I spoke too slow. Next time I will be quicker again. So back to you, Winnie.
Thank you, Ingo. Now the speed of your voice was very, very well today. We came now to, let me check, to the Q&A session. Hold on a second. So, at first, I'd like to thank Ingo for his presentation, and I will come to Chris. Chris, did you receive any questions so far?
Yes, actually, we got quite a few of really nice questions. So let me start by reading the first one here. So in which version of PikeOS are these functionality available? I'm not quite sure what is referenced by this functionality. I would assume either it is the separation capability, which PikeOS has from the beginning on. It actually is a separation kernel by construction, so all this MILS approach will be supported by any PikeOS version. If you are referring to the functionality of adding the AUTOSAR Adaptive, this is a specific new product which will be sold and distributed by Vector, and this is a bundled product, so you don't purchase the parts independently. It is an AUTOSAR adaptive product that you can buy, and then you have all the components available. The next question I have here is there any resemblance between MILS and a typical hypervisor? Does MILS use any hardware resistance for its features, for example, hardware virtualization? So, yes and no. MILS approach is a method to separate things. So the idea of separation and compartmentalizing the system so that you have more simple parts that you can handle more easily. Now, separation is then very close to actually what a hypervisor does, because it also separates and creates a very isolated environment. So with PikeOS, yes, you have the separation capability, but that does not mean you have to use some kind of guest operating system, but you can. So you have both the separation capability as well as the hypervisor capability, and when we are in hypervisor mode, so where you have a partition where you're running, for example, a complete Linux guest, then on ARM hardware we can also use the hardware virtualization features that ARM provides. Next question I have here is, does PikeOS run in privileged mode or can run partly in user mode? So actually PikeOS is a microkernel, so the kernel part of PikeOS is running in privileged mode, so also only a very small part of PikeOS actually only runs in privileged mode. If you go back to the slides that we will provide later on and look at the architecture diagrams, you'll see that we actually split PikeOS always into two parts: the PikeOS kernel and the PikeOS system software. So only the kernel runs in privileged mode, and already the system software runs in user mode, as well as all other applications on top of that. So in a sense, the major part of the system is running in user mode, while only very small parts are in privileged mode. Then the follow-up question to this one was, what is roughly the percentage of OS execution time spent in privileged mode? That's hard to say, because it very much depends on what your applications do. If your applications call kernel functions or functionality of the kernel a lot of time, then of course more time is spent in the kernel. If your applications are mostly busy doing calculations or other arithmetic things, or not using any of the OS functions that PikeOS provides, then the time spent in the OS is close to zero. So there's no general overhead introduced other than any operating system would introduce. So yeah, it's there's no real one number that one can give. It depends on the application profile. Yeah, so that was the questions I got here.
Yeah, thank you, Chris. Ingo, the same question to you. Did you receive any questions you can answer?
Indeed. Here's one question of the quantity of code coverage that is expected for different ASIL levels. So I'm pretty sure that Chris knows the answer too, because they are the safety experts. And from my understanding, in ISO 26262 for QOM, there's no specific requirement regarding code coverage, but it's of course always good for software quality to measure code coverage to see which lines of code were not tested yet, not executed yet. And then if we go up to ASIL A, we need statement coverage. In ASIL B and C, we need statement and branch coverage or statement and decision coverage. And in ASIL D, we need statement, branch, and MCDC coverage. Correct, Chris? Are you still there?
Yeah. Yes, that I think was correct.
Thank you.
It gets more complex the higher you go, and it tests vastly more tests and vastly more time. So higher levels get very much, very quickly, very expensive.
Yes. Then here is a question: does VectorCast show the percentage of coverage or the lines of code which are covered? Yes. We show both. A question to the requirements gateway that I showed. In this example, they asked for doors, if we can also export the linked test cases back to doors. And yes, we can. Not only for doors, but for all requirements management integrations. We can not only import the requirements, we also, so after you linked the requirement to a test case, we can export the test cases back to the requirements management system, and also the linkage between the requirement and the test case, which is very helpful for traceability purposes. For doors, so I'm not an expert on that integration, because here's a question on how is that solved. We access, well, more or less the doors database directly using, I think, the DXL scripts or something like that. This is implemented in Python. We did have one customer who said they don't want other tools to directly create things in their productive database, so you can always use the CSV export and then kind of manually import it from a CSV file into DOS. But the standard implementation in our case with DOS is that we automate this using, I think, DXL scripts or commands in DXL files. Any more questions? There is a question: what platforms are supported? I'm not sure to what platforms you're referring to. So we have VectorCast for Windows and for Linux, and for Solaris traditionally. If platforms mean different chips or different boards, then we understand the compiler. We rely on the compiler, and the compiler does the compiling for different boards. So we don't care too much about whether it's an ARM chip or PowerPC or different other chips. Also, whether you want to test bare metal or using an operating system is not important. VectorCast. A question on the command line interface. Yes, there is a command line interface, so everything is perfectly automatable, and you can use it with continuous integration tools. And then there is a question on Qt or Qt, as the Qt people say. So whether we support Qt, and yes, we do. We understand very complex C++ code, also the Qt frameworks, because we're using a parser, a commercial parser. The EDG parser is used by VectorCast, so we understand very complex C++ code. I think that it's everything from my side.
Yes.
Actually, Winfried, if I may, there was one question coming in right now that I didn't see before. If we still have the minute, I can just quickly give that an answer as well. So it says here, hello, Chris, you said non-interference is guaranteed between apps. When it comes to memory, it is clear at different address spaces, but how would you solve the resource starvation issue in pseudo real-time OS environment? What is the scheduler in use? So yes, correct. Resource partitioning is essentially controlling the address space, because everything is address mapped. All accesses refer to some address mapping. So once you're in control of that, you can give access or deny access to certain resources for specific partitions. If you're looking at the time domain, we are using a scheduler that is based on time partitioning. So actually we have different time windows that need to be defined, and then those time windows will be assigned to resource partitions, so that partitions can run for the defined amount of time that is provided from the scheduling scheme. You can have multiple different scheduling schemes between which you can choose and switch back and forth from, so there's some flexibility there. We don't do any dynamic scheduling. It's, as I said, based on time partitions, and within the time partitions, then there's a priority scheme that is going on. So yes, if one of your resources is starving, then it's an architectural mistake by not providing enough computation time in your scheduling scheme that you have to define.
Last question from my side about needed coverage. Does it have to be 100%? Well, that's my understanding. It has to be 100%. If you only have 97% of code coverage, then you will have to tell your certification authority what about the 3% of code that you did not cover, and that's why CBA, or covered by analysis, is a nice feature to have, because you can add the coverage to your reporting tool, and then you have 100% code coverage. That's it. Thank you.
Yes. Now we have to come to the end of this webinar. I think I'd like to thank Chris Berg and Ingo for the presentations, and SYSGO for the support to make this event happen. I'd like to thank all attendees for your interest and the time you spent with us today. We hope you enjoyed this webinar, and we can welcome you again at one of our next webinars. We wish you all a great day and a successful rest of the week. Goodbye.